To properly analyze what happens to a spinning top over time, we need to take into consideration what forces are acting on the top and in which direction. Then we can begin to answer the question why the top eventually stops spinning. We can see from this diagram the top consists of a rod fastened normally through the center of a uniform circular disc and is free to pivot at its origin. The top has axial symmetry and rotates about the z-axis with angular velocity. The force of gravity acts in the downward direction from the object's center of mass. The angle at which the top can pivot is the precession angle. Gravity is felt by the top with respect to this angle and can be used to define the torque. The spinning top is a form of a rigid body. Therefore, it is made up of many small particles a constant distance away from each other. The center of mass of the top can be thought of a point where all the weight is evenly distributed and is measured relative to the origin. From this point, we can also measure the momentum. The interesting thing about some rigid bodies is that there are two forms of momentum which can act on a body, that is rotating and spinning at the same time. The total angular momentum, which correlates with the spin, and the total momentum of center of mass, which correlates to the motion of the center of mass, also known as translational motion. Together, the two can be put together to give total momentum. It's important to note the momentum and torque are perpendicular to one another. If we were to spin the top to the right with angular velocity, using the right-hand rule, the torque would actually act going into my screen. The two equations we will focus on are the angular momentum and torque. Angular momentum is defined as the inertia times angular velocity for each axis. As mentioned, the torque is due to gravity and the weight of the top. If we were to envision the system without gravity, momentum would be constant and the top would spin indefinitely. Since the existence of torque implies a change in momentum, we can equate torque to change in L, or L dot. Deriving a bit further, we can find the angular velocity in the z-axis. But torque is perpendicular to momentum, so momentum changes in direction and not magnitude. This is why as the top is spinning, it tends to wobble as it slows down. Eventually, momentum cannot keep up with the torque, and the precession angle increases as it slows down until it can no longer keep itself upright and falls. If we were to plot angular momentum over time, we would see that momentum is conserved and eventually would give us slower speeds. The idea of precession angles can also be used in other scenarios, such as the spin of the Earth. The Earth is inclined at an angle of 23 degrees. Just as the spinning top felt torque, the Earth also feels torque from the Moon and the Sun. I've also created this video so you can see in a bit more detail exactly how these forces work. Here we can see this top is beginning to wobble. The angular momentum is slowing down, and the angle of precession is beginning to increase. And it continues to do so until it falls.